Hi guys. I hope you are well. Welcome to our last part of grade 11 Euclidean geometry. This is part 8 out of 10. The last two parts will be based on grade 12 content. Okay, so you don't have to check that out if you are still in grade 11. Right, so in this video we are going to apply all the theorems that we have learned and also learn how to use the converses, whether to prove that something is a cyclic quad, to prove that the line is a tangent, to all those type of problems, right? The higher order thinking ones. Right, so let us look at this one. This is adapted from a textbook whereby we are told in the textbook they tell us that O is the center of the circle. Okay, so O is the center there. Okay, P, Q, R, and S are points on the circumference of the circle with center O, like I just said. So we are given the center in this case and all the other points on the circumference. SOQ, where's SOQ? SOQ is this line that goes through the center. In fact, SOQ by default, this is a diameter. Remember we said a diameter is what? Is a line that goes from circumference through the center to the circumference. So SOQ is a diameter. Okay, and then what else do we have? PO is parallel to SR. Where's PO? PO is that radius there, and then we have SR right there. Okay, so OPR is 24 degrees. Where's OPR? Where is it? Here we have O. Where's P? P is there. Where's R? This angle right here. OPR, angle P1 is 24 degrees. Determine with reasons the size of the following angles. The first one, which is angle R1. A friend of mine once told me that if you want to work with this thing in simple terms, first highlight all the angles that are equal to each other before you even look at the problems. So go to the diagram and start marking things. Right, the first thing that I'm seeing is that this is going to be a 90 degrees because we said SOQ is a diameter. Right, now let's check other things. We can see that this angle right here must be equals to that angle there. Those are alternating angles. We have parallel lines there. What else do we have? We can see again that this angle R1 is going to be that angle Q1. If you look at it, those are angles in the same segment. They are both subtended by what? They are subtended by the arc SP or PS. Right, which other angles can we find? Angle at center. Yeah, we do have angle at center. In fact, angle at center, this angle O1 will be twice Q1 because SP subtends angle O1 at the center, but the very same SP subtends the angle Q at the circumference. Okay, yeah, so let's answer all those questions. First things first, determine with reasons the size of angle R1. We have to find angle R1. Right, we have angle R1 already. Look at the parallel lines. We have that this line is parallel to that line, which means if we follow alternating angles, angle R1 will be equals to angle P1. So angle R1 equals to angle P1, and they are both equals to 24 degrees. And these are what? These are alternating angles. Alternating angles since the line OP is parallel to the line SR or RS. Right, like that. So this is number one. Number two, which angle are they looking for? Angle R2. Remember we said the whole of angle R is going to be equals to 90 degrees because these are angles in a semicircle or angles on a diameter, right? So, but angle R is made up of two angles, which is angle R1 and angle R2 added together. So this is 90 degrees. We have found angle R1 to be 24 degrees plus angle R2. And in fact, angle R2 will be equals to what? 90 minus 24. Like that. So we have 90 degrees minus 24 degrees, which gives us that this is equals to 66 degrees. In fact, let me write it here. That's 66 degrees. We have this one to be 24 degrees. Yeah. Should I write the reasons? No. Let me erase this right here because you have got it. And then angle O2, let's find angle O2. How are we going to find angle O2? If you look at O2, tracing back with your index finger will give you the following now. Let's do it. Angle O2, which is this angle right here. If you trace back, you will see that angle O2 was subtended by that arc PQ or chord PQ. but the very same PQ goes on to subtend another angle at the circumference, which is angle R2, as you can see now. In fact, angle O2 will be equals to twice angle R2, and this is what? This is angle at center, which is equals to angle at center being twice angle at circumference, like that. Okay, so 2 times 66, like that. So this gives us what? 66 times 2, which is 120, 132 degrees. Right, so O2 is 132 degrees. Let's find angle P2. Where's P2? P2 is that angle right there. If you look at this, you will see that on P2 you have this triangle right here. I told you, never miss a step. So when you follow this triangle right there, you will first see the following, that actually this line is equals to that line. The line OP will be equals to the line OQ, sorry. OP is equals to OQ, and this is a radii, right? But remember, we just calculated this and we got 132 degrees. This means that the angle P2 will be equals to angle Q1. Why is that? These are angles opposite equal sides. Right, so we can go ahead and calculate angle P2, because if we do sum of angles in that triangle, angle P2 added to angle Q1 plus angle O2, this should give us what? It should give us 180 degrees, and these are angles in a triangle. Right, so P2, do we have P2? But we know that P2 and Q1 are equal, so we can just write this as 2P2 plus the 132 degrees, which is equals to 180 degrees. So P2, which is equals to what? Which is equals to 180 degrees minus 132, all divided by 2. So it's 180 minus 132, which gives us 48. 48 divided by 2, which is 24 degrees. So we have this. You see how long? You see, like, I took a very long step only to find that it's just a 2-mark question. You can do this. You are allowed. Okay, don't skip steps. Once you start skipping steps, that's when you lose marks. Write all the necessary steps that help you get to the answer. Okay, so let's look for the other one, angle S. Where's angle S? Angle S, which is this one right here. Let's think about it. How can we find angle S? What's the best way to find S? How possible is it to find Q2? But in order to find S though, let's check. If we trace back on S, we will see that this angle was subtended by that arc there, this one, and the very same arc goes on to subtend another angle which is equals to angle P. So we can go for that. We can see that in fact angle S is equals to angle P. But if you look at angle P is made up of P1 plus P2. Alright, and what's the reason for this? These are angles in the same segment. Right, like that. So this is angle S, which is equals to, remember we have 24 between those two, is it? Yeah, we got 24 even for that. 24 times 2 plus 132, which gives us 180. So angle S is P1, which is 24, plus P2, which is 24, giving us a 48 degrees. Right, and then lastly we are asked to calculate Q2 being that, but we already have the 48 right here, so Q2 should be easy. In fact, angle Q2 is equals to 90 degrees minus 48 degrees, and those are angles in a triangle, angles in this triangle right here, as you can see. Right, so it's angles in a triangle, and then we get this, which is 90 minus 48, giving us a 42 degrees. So that's how you apply this. Moving on, let's look at another problem. Get this one, which needs you to prove things now. So A and B lie on the smaller circle. We have two circles there. D and E lie on the bigger circle, and C and F are points of intersection between the two circles. So the two circles overlap right there at C and F. Right. What else? A, B, G, where's A, B, G? A, B, oh, here's B right here, because they say let B1 be X, but they didn't label that. But since we see the X there, then we can see that B1 is that. Okay, A, B, G, that line, F, C, G, that line, E, D, G, all those ones are all straight lines, and A, F, E, we have straight lines there. Okay, let B1 equals to X. Determine with reasons two other angles equals to X. How can we work that out? two other angles equals to x. Here I see a cyclic quadrilateral on the smaller circle. As you can see, they told us that this is a straight line, which means this exterior angle of that cyclic quad equals to the interior opposite, or the angle in the alternate segment. So angle B1 will be equals to angle F1. Angle B1 is equals to F1, and they are both equals to x, and this is exterior angle of a cyclic quad. Right. And what else? We have to find another one. Which other angle is equals to f? Now, after relating it to f1, now I'm looking for one that is equals to f1. As you can see, we have another cyclic quadrilateral on the bigger circle. Now remember, they told us that this is a straight line, so f1 is equals to the interior opposite angle. So angle d1 is equals to angle f1, and they are both equals to x. Again, this is the exterior angle of a cyclic quad, like that. Okay, so let's move on. We now have two angles that are equals to x. Let's mark those. This is x, and this is also x. Determine with reasons. Okay, done with this. Number 2, prove that BCDG is a cyclic quadrilateral. Where's BCDG? B there, C, D, G is a cyclic quadrilateral. Listen up. Whenever you are asked to prove that something is a cyclic quad, you first need to look at it. There's multiple ways you can prove that something is a cyclic quad. Right. The first way, if you can see that the exterior angle of that quadrilateral is equals to the interior opposite, or the angle in the alternate segment. Let's say you have something like this. If you're able to prove that this angle right here is equals to that, then you can conclude that this is cyclic. Right, there's an imaginary circle that goes through that. There's a circle around that, not imaginary in fact. Or if you can prove that if maybe this angle is A and that's B, when you sum them up, when you add this to that, if you add angle A plus angle B and you find that they equate to 180 degrees, then you can conclude that it's cyclic. In some instances, you might even have to use you might even have to use angles in the same segment. If you are able to prove that this angle that is subtended right there is equals to that angle that is subtended there, then you can conclude that this is also cyclic. So in all cases, you first need to evaluate the situation that you have and think about all possibilities, or the statement that can allow you to conclude. First things first, if you want to prove using exterior angle of a triangle, the first option that you have, if you can prove that angle B2 is equals to angle D2, if you can prove that this angle right here is equals to that, because this appears to be the exterior angle of a cyclic quad, then you can conclude. That's option number 1. Option number 2, if you can prove that the angle D1 is equals to what? Is equals to the interior opposite angle D1, and angle B1 being equal to each other, then that can also allow you. Angle D1 being equals to angle B1. What other options do we have? If we can prove that angle B1 added to angle D2 gives us 180 degrees, then this can allow us to conclude as well. What other option? Look at G. If we can sum up G with C, that's C there. If we add up angle BCD, this one right here, to angle G and get 180 as well, this can allow us to conclude. Now, amongst the options that we just came up with, choose the one that is easiest. Right, and we can see if we try this one of D1 and P1, because we already calculated D1, we were given P1, so we have this. We can therefore say angle D1. All right, let's take that one. We have what? Angle D1 being equals to angle B1, which is both equals to x. This is proven. All right, then you can conclude that actually BCDG is a cyclic quad. BCDG is cyclic. If you look at this, we used something related to the exterior angle of a cyclic. Then the reason will then be what? Converse of what? Converse exterior angle of a cyclic quad. Like that. It's the converse now. Remember, a converse, we said what we actually mean by a converse in simple terms. If A implies B, then B implies A. Right. If you have eaten, it means you are full. If you are full, it means you have eaten. just like that. So yeah, let's look at number 3. Join PD and then prove the following. Okay, now once you are able to prove that this is a cyclic quad, remember we have this to be x as well. Once you have proven that it's a cyclic quad, you can draw the cycle there. You can have the cycle around that. Of course, sometimes it's a bit difficult to draw it, but yeah, there we have it. That's our cycle. Right, it doesn't have to be perfect because, hey, joining all those points. There's our why did I shade this? No shade. I want to change the color into green maybe. Yeah, yo, just became worse. Okay, I'll leave it as black. Join BD. Where's B and where's D? Oh, we have B here. They say we should join those two. Let's use a dotted line so that we can differentiate. Join BD and prove what? Yeah, and then prove that GBD, what's G? GBD, which is this new angle right here, is equals to angle E. There's angle E out there. So now we need to strategize. How can we find this? We can find that because first things first, if we look at the bigger circle, we can find this angle which is C2. Look at C2. C2 is equals to E because of what? Exterior angle of a cyclic quad. You can see that this angle is equals to that angle there. Okay, so angle C2 is equals to angle E. Angle C2 equals to angle E, and this is exterior angle of a cyclic quad. And then what else? We have, but if you look at this, you will see angle C2 was subtended by that arc or chord GD, and then the very same arc now goes on to subtend another angle there. Can you see this angle and that angle are equals to each other? So that angle, which is called GPD, GPD will be equals to angle E. In fact, it's not equals to angle E, it's equals to angle C2, right? And then this is angles in the same sec. All right. And then lastly, we can see that, listen up, if A is equals to B, but B is equals to C, then it means A and C are equals to each other. Same thing. You can see that C2 is equals to E, but also C2 is equals to GPT. Therefore, it means GPT will also be equals to angle E. Why? Because they are both equals to angle C. Both equals to angle C2. Then that's that. We have proven this one. Right. Secondly, prove that the angle... Oh, that's a mess. Let me try to erase some stuff here. Yeah, fair enough. This is still x. D1 is still x. Prove that the angle BDG. What's B? Oh, we still have that line there. BD. What's G? Oh, this angle right here. BDG, which is this angle here. It's not D2. It's part of D2. BDG is equals to angle A. This one is equals to that angle over there. How can we work this one out? I think it follows the same approach as the previous one, because we can prove that actually the angle C3, can you see angle C3? If you follow this cyclic quadrilateral, the one that I'm about to highlight in green, let's use a green. Right, if you follow this cyclic quadrilateral right here, you can see that the exterior angle of that is actually the angle C3 there. So this angle C3 is equals to what? This angle C3 is equals to none other than angle A. But the very same angle C3, if you look at it, it's subtended by which this chord right here goes there, this chord goes there. So angle C3 was subtended by BG, but the very same BG goes on to subtend the angle that they are looking for, that one, which is BDG. So you can see that BDG will be equals to C3, but C3 is equals to A, so it makes A equals to BDG. Then you are done. Okay, what type of quadrilateral? Okay, now this needs a bit, needs you to know a bit about shapes. That's for you to do. Okay, here we go again. Here's another one. Listen up. If you ever attempt a problem on Euclidean geometry and you find that you don't see anything midway through, go back to the statement and reread again. Reread it multiple times until it makes sense, right? And stop this tendency of trying a problem without reading a statement. It doesn't end well. Read the statement, highlight important things. The diameter 8G, already I have a diameter which is 8G, then I have a 90 degrees there, right? But then I have another one, 90 there, because you can see that those two, this diameter subtends that angle F, that F angle there, and also D2 there, right? EC is a tangent. Remember tangent. So there's EC is a tangent to the circle at D. Tan-Cot theorem tells us that the angle D1 is equals to the interior opposite angle, or the angle in the alternate segment, which is A1. Right, we are done with that. A, D, G, and F lie on the circle where DC is equals to BC. What's D? DC is equals to BC. Once I have DC being equals to BC, then I'm already marking those two angles opposite equal sides. B1 and D1 should be equal to each other. Right, AFB is a straight line. Let A1 equals to X. Now let's work with this. Number one, prove that ADCB is a cyclic quadrilateral. ADCB, this whole thing, prove that there's a circle that runs around the entire thing there. There's a circle that goes something like this. That's what it's DC. You see, like I said, sometimes it's quite difficult to draw the circle, but you have to try. Right, for me it's gonna be easier because I'm using inbuilt functions, but for you with the pen, you won't know where the center is. That's the issue. So I can just move this around until it fits all the corners there. Let me see if I'm able to accommodate this, then I can try out those ones. Yo, this is harder than I thought, even with inbuilt functions. Okay, but it's something like that. Or let me just draw it freehand. Remove this and just join that, because this must also join in. So it should go from there, go there, go there, join this as well, and then like that, something like this. Right, to prove that it's a cyclic quadrilateral. So what? A, D, C, B. Let's think about the options that we have now. First of all, if we wanted to use the exterior angle, if we can prove that D3 is equal to the whole of B, let's mark the options. You can either prove that D3 is equal to angle B. That's number one. Let's check another one. Which one? What else can we prove? If we can prove that the angle A, when added to angle C, will give us 180 degrees. And also, if we can prove that the angle B, when added to that one, D1 and 2, right? Sometimes we can write it as D1 plus 2, will give us 180 degrees, sorry, because those are opposite angles of that quadrilateral. What else can we prove? Okay, now here's another option that I added, right? The one we spoke about earlier on. If you are able to prove that the angles that are subtended by a line are equal, look at DC. DC goes on to subtend that angle which is A1, and it also goes on to subtend that angle which is B1. If we can prove that angle A1 is equal to angle B1, that can also allow us. That's not the only one. Even if you can prove that this angle B2, which is subtended by AD, is equal to that angle C1, which is also subtended by AD. So if you can prove that B2 is equal to angle C1, then you are sorted. And not only limited to those, there's many of them. Now you need to select which one is the easiest for you. Okay, find the one that is easier to work with, and we already have the answer anyway, because what we said is, from the Tan-Cot theorem, we have the following. Tan-Cot theorem tells us that angle A1 is equals to angle D1. Right, we have this tangent which is CD, and then the angle between a tangent and a chord equals to the interior opposite, equals to X, and this is Tan-Cot theorem, right? So at least now we have an X there, but we spoke about it. Remember, it was given to us in the opening statement that the line BC, DC is equals to CP, so BC is equals to CD, right? This is given. Therefore, we can prove that the angle B1 is equals to angle D1. How? These are angles opposite equal sides, and by default this means that, remember, we just found D1, to be x, so this is also x. Like we said, if you can prove that the angle x, which is subtended by this chord DC, is equals to the angle that, if you can prove A1 is equals to B1, then you are sorted. So angle A1 is equals to angle B1, right, which is equals to x, and this is proven. Then you can conclude now that actually that ADCB is cyclic. Why is it cyclic? Then you can either say that it's the converse of what? Of angles in the same segment. There's two options. You can partially state the theorem. So converse angles in the same seg. Alright. Or it can be angles in the same segment equal. If angles in the same segment are equal, then it means like that is a cyclic quadrilateral. Makes sense. So if this is a cyclic quadrilateral, then you can use those conditions from now on. Right. Prove that AC bisects BAD. So there we have it. AC is this line right here. You need to prove that the line bisects BAD. Now how can you do that? Listen up. This question is easy. Of course, you are required to prove that AC bisects BAD, but in simple language, you are basically required to prove that this angle right here is equals to that. Angle A1 is equals to angle A2. That's what they want you to prove. But we know that angle A1 is equals to x. Now the biggest question is why? Why is A2 equals to x? Why is angle A2 equals to x? Because we already know A1 to be x. So now we are going to do whatever geometry necessary until we prove that A2 is also equals to x. Now this is easy because if we do a trace back there on A2, look at the following. A2 was subtended by this chord which is DC. There, the circumference of the circle, the bigger circle we constructed. Remember, after proving that this is a cyclic chord, it means there's a circle there. You can now use everything that applies in circles. And then from here, the very same chord subtends another angle at the circumference, which is D1. Can you see? So it subtends this angle and that angle. So by default, since they are subtended by the same chord, then we can see that angle A2 is equals to angle D1, but we proved that D1 is x in the previous statement. They are both equals to x. Now the reason for this is what? Angles in the same segment. In the same set. Then we can see that angle A1 is equals to angle A2 and they are both equals to x. This is proven. Therefore, what? The line BAD, sorry, the line AC, not BAD, the line AC bisects BAD, which means now we have an x even for that. So you see, that's how it goes. Let me remove this to make up space. Yeah, that's what we have. More problems. Prove that DG is equals to FG. What's DG? There. This is the line DG. Let me just use a different color to highlight that. And let me remove some of the things. It's becoming messy now. Here. Prove that DG is equals to FG. Where's FG? F is there. G is there. Yo! Prove that DG is equals to FG. How can you prove that DG is equals to FG? Okay, you can prove that DG is equals to FG, but this requires you to know the properties of shapes, right? That's the first issue. So, if you look at this now, it looks like a kite, the overall shape that we have, ADGFA. Yeah, ADGF, that looks like a kite because we have those opposite angles, those two being equal to each other. Right, and then we have, remember that this should be bisected. So basically this should be a kite. And if it's a kite, one of the properties of a kite is that both pairs of adjacent sides are equal to each other. So this is equals to that. So by default, ADGF is a kite. Right, go and look up the properties of a kite, then you will know how I got to that conclusion. Right, and then therefore, DF DG equals to a GF, right, adjacent sides Adjacent sides of a kite. Those are the adjacent sides of a kite. Okay. Done with this. Determine with reasons the size of angle C2. Where's C2? Let's locate C2. C2 is right here. You can find C2 as well, because now you need to trace back. This whole trace back thing works a lot. Okay, so you have C2 right here. When you trace back, you will see that C2 was subtended by that B and A right there. And then the very same chord AB goes on to subtend another angle, which is D2 right there. So in fact, C2 and D2 are equals to each other. But we do have D2, so we start there, because there's nowhere where we wrote it. Angle D2 is equals to 90 degrees. And this is angles on a diameter, or angles in a semicircle, right? Then we have it. Angle D2 is equals to angle C2, and they are both equals to 90 degrees. And these are angles in the same sec. Okay, so there we have angle C2. Prove that angle G1 is equals to O2. Where's G1 first? There's angle G1 right there. We first need to find angle G1, or we need to find O2, one between the two. We either find angle G1 first, and then we find O2. And a G1 seems like it's a bit difficult to find. Oh, it's easy to find G1, because we have a cyclic quadrilateral right there. And they told us that this is a straight line. Since this is a straight line, then by default, this exterior angle of that cyclic quadrilateral is equal to the interior opposite. So we can start right there and do what? And make a conclusion that actually the angle G1 will be equals to the angle A as a whole. But remember, A as a whole is x plus x, so it's 2x. And this is the exterior angle of what? Exterior angle of a cyclic quad. Alright. Now, we need to ask ourselves, remember we are trying to prove, we are required to prove the following, that angle G1 is equals to angle O2. Now the question is, the biggest question that we are now facing is, since angle G1, since we just proved angle G1 to be equals to 2x, here's the question, why? Why is angle O2 equals to 2x as well? Because we are trying to prove equality between the two. So if this is 2x, this is bound to be 2x as well. Then we can now know what we are working towards. Right, let's go back. If you look at that smaller circle there, this is a radius. This is a radius right here. This is also a radius. This allows us to conclude the following. We first have that OA is equals to OF. That's a radii, right? Which then gives us that the angle F3 will be equals to angle A2, and they'll both be equals to x. And these are angles opposite equal sides. Right. So once we have an x even for this, then we can find O1, sum of angles in a triangle. Angle O1 is equals to 180 degrees minus x, so it's minus 2x. And these are angles in a triangle. Right. And then lastly, we can find angle O2. That's a straight line. Angle O2 is in fact 180 degrees minus angle O1. Angles on a straight line. Right. Like that. But we do have angle O1. Angle O1 was calculated there. So this is 180. It's 180 minus 2x for O1. This gives us 180 minus 180 when we expand that. This times that, which is positive 2x. This cancels that, and it gives us the 2x. Now that's why angle O2 is equals to 2x. Therefore, G1 is equals to O2, and they are both equals to 2x. Makes sense? That's how you do it. Prove that FBCG is a cyclic quad. What's FBCG? Let's look for that. FBCG is a cyclic. There you have it. It's FBCG is a cyclic quad. So, which is easy stuff. You can think about all the options you have, but remember they told you this is a straight line. So if you can prove that this angle, which we said is going to be 90, is equals to that, then you are sorted. And you've already proved this. Remember we said this is a 90, which is equals to that C2. We said even C2 is a 90 degrees angles. It was angles in the same segment. So if we have a 90 here, we can prove that to be 90 degrees. In fact, that angle AFG will be equals to 90 degrees as well. Why? it's subtended by a diameter, so it's angles in a semicircle, but that very same angle is equal to C2. Then the reason why this whole thing is a cyclic quad, converse exterior angle of a cyclic quad. Makes sense? So that's how it goes. For what value of x will DC be a tangent to the circle? Let's see, where's DC? Will it be a tangent to the circle through F, B, C, and G? Where's F, B, C, and G? For what value of x will DC be a tangent? I'm not sure if I get this. Wait, let me check. For what value of x will this be a tangent? What does this mean? For what value of x will DC be a tangent to that? Because if you look at this, if this were to be a tangent to this whole circle that runs through that goes there, in order for this to be a tangent, this angle right here, C1, should be equals to B1. Tan-Code theorem would work in that case. So I think that's the question. For what value of x will DC be a tangent? If only C1 is equals to x, then this will be tangential. That's what I think. Okay, I hope it sheds some light. Yeah, exam type questions as well. Here we have one. In the diagram, EA is a tangent. I love tangents. If they give me a tangent in a center, then I'm satisfied. EA is a tangent. That's a tangent there to the circle ABCD at A. AC is a tangent to the circle at, where's AC first? Oh, AC is this one, is a tangent to the smaller circle, so we have another tangent there. Right, let's see. That's just intersection points. A1 is equals to x. Where's A1? A1 is right there. Prove the following, that BCG is parallel to AE. Yo, required to prove that BCG is parallel to AE. This is what you are trying to prove. This is your statement, but this is their statement. Let's come up with our own statement. Let's highlight the lines we are trying to prove that they are parallel. Where's BCG? There's BCG is right there. Is parallel to AE. There's AE. Now let's look at this thing and think about what can allow us to conclude. If these were to be parallel lines, the first thing we would need in order to conclude, if we can prove that this angle is equals to what? That angle, they are in alternating positions. If we can prove that angle C1 is equals to that angle CAE, that's the first one, that's the first option. Or if we can prove that the angle A3, again, alternating angles, this one alternates with that, is equals to GCA, the angle GCA. That's another statement that can allow us to conclude. What else? Let's look for another one. Those are not the only ones. Or if we can prove that when you sum up this and that, you get 180 degrees. Remember, these are co-interior angles, right? Or if you can prove that this angle right here is going to be that angle there, alternating angles, provided that this is parallel to that, that can also work, right? And there's multiple of them. Even if you can prove that G2 is equals to A1, that one is still applicable, right? So you choose the best one that's going to work out for you. Not just the best one, just choose the simplest one. Okay, since we have a tangent, let's work through this. We can see Tan-Code theorem tells us that we can get C2. In fact, C2 is equals to that, because remember we said for a Tan-Code theorem we need that triangle to touch the circle at 3 points, or the circumference 3 times. So Tan-Code theorem, there we have it. A1 is equals to C2 and they are both equals to x. Right, so angle A1 is equals to angle C2 and they are both equals to x. Why? That's Tan-Code theorem. Okay, so that's Tan-Code theorem. Right, so we have an x here. Does it prove what we are trying to prove though? Not yet. Right, it doesn't prove it as yet. Let's see, what else can we do? What else can we work with? We can still use Tan-Code theorem again, because now if you look at this, you will see that here we have another triangle there, and remember they told us that this is a tangent, so this angle right here is equals to that interior opposite angle. So angle C2 is equals to angle G2. Angle C2 equals to angle G2. But remember, angle C2 is x, which means G2 is also going to be x on what? On tan chord again. This is tan chord theorem, right? So even for this we have an x. Remember, this was one of the options we had previously, whereby we said to prove that this is parallel to that, we can at least have alternating angles, where if we can have alternating angles right here such that this is equals to that. So now we have successfully done that. We have proven that angle G2, the angles that are in alternating position are equal, which is equals to x. Then this is proven. Therefore, you can now conclude that the line BCG is now parallel to AE. You need a reason for that. Why? Because alternating angles are equal. Alternating angles equal, it means the lines are parallel. And once you have done that, do not forget to mark that those lines now are parallel. You can use those conditions and forget about this. Remember, this was just trying to help us shape our argument. Right, let's make up space. Now, what else? AE is a tangent to the circle FET. Where's AE? There's AE. Prove that this is a tangent to the circle, which is what? Which is FET, which means somewhere right here where you find FET, somewhere here, right, somewhere here, right, on the circle that touches FE and D, there's a circle that runs there. And in order for you to prove that there's a circle there, what should you do? If you can prove that this angle E1 is equals to that angle F1 there, because it looks like the converse of what? Of tan chord theorem, then you have successfully done that. You have successfully proven. So let's go ahead. Now the question is why? Why is angle F1 equals to y? That's the reason we need. If we can prove that, then we are done. Let's go and look for it. Let's go and find out why that angle is equals to that. So we structure our argument now. If you follow from there on the parallel lines that we just proved, we can see that this angle E1 is equals to C3, alternating angles, right? So angle E1 is equals to angle C3, right? But E1 is equals to y, so even this one is y. This is alternating angles. Those are alt angles since what? Since the line now, that line BCG or BG, since that line BCG is parallel to what? To AE. So now we have this angle right here to be y, at least. But then if you look at this, you will see that here we have a cyclic quadrilateral and we have this straight line right here. The exterior angle of a cyclic quad should be equals to the interior opposite angle. Okay, not quite helpful. Oh, sorry, not this one, but the other one, because this one is equals to the interior opposite, it's equals to that. But this one, remember we said now we are coming from this direction, we do what? We skip this, we take that. So F1 is equals to what? F1 is equals to C3 based on exterior angle of a cyclic quad. So angle F1 is equals to angle C3, but angle C3 was proven to be y, and this is the exterior angle of a cyclic. Now if you look at this, you will see that since we also have a y here, we have successfully proved what we were trying to prove initially, right? So angle E1 is equals to angle F1, and they are both equals to y, or proven. Then we can conclude that therefore therefore AE is a tangent to circle FED. Let's just write it in full. To circle FED. Why is that? Because of what? Of the converse tan chord theorem. And we are done. And now we can conclude that there's a circle there. We can even draw it so that you may use it at some point. Prove that AP is equals to AC. Where's AP? There's AP. Is equals to AC. There's AC. Prove that these two are equals to each other. Again, you need to structure your argument. Listen, the question asks you to prove that AP is equals to AC. You come up with your own statement, your own sub-statement, and you say, basically, I'm required to prove that the angle B is equals to the angle C1, because that's the only reason which can allow you to conclude that those sides are equal. Angles opposite equal sides, or sides opposite equal angles. If two sides are equal to each other in a triangle, then those angles that are opposite those sides are equal. If two angles are equal to each other in a triangle, then those sides opposite those angles are also equal. Right, so now we need to figure this out. Let's look at that. At least we have multiple things. If you just base your focus here, you will see that actually angle C as a whole is made up of what? Is made up of that C. If you add up C1, C2 and C3, you get 180. Angle C1 plus angle C2 plus angle C3. This should give us 180 degrees, and these are angles in a straight line. Alright. And we do have C2 and C3. So we are looking for C1. C1 plus C2, which is X, C3, which is Y. This gives us 180 degrees, which means angle C1 is equal to 180 degrees. Put a bracket there into X plus Y. When you transpose both of them, you get that. Now here's the famous question. Why? Why? Because you now have C1, which is that. Why is angle B equals to 180 degrees minus X plus Y? We need to go and prove that. Why is angle A equals to that? We need the reason for that. Okay, so let's go and look for it. Not angle A. Why is angle B equals to 180 minus that? Let's work on it. It's the first thing we can see there. No tangents whatsoever. Nah, that's not working out. Whew. This is gonna be a tough one. Well, it's not so tough after all. Well, you know. Because if I look at this, it's just that I'm going to take a very long route. My mind tells me that since this is a tangent right here, this whole angle right here, which is A1 and A2, will be equals to angle B. Now the issue is finding A2. Of course, it's easier to find A2, because now if I focus on this whole triangle, which has more information, this one, if you focus on that triangle, which is CGA, you can see you have those two angles there, which is Y and X. You have G2, which is X. You can find A2. So basically angle A2 will be equals to 180 degrees minus all those angles, minus into what? Into that C2. So it's 180 minus C2 minus C3 minus G2, like that. So all those angles, which will give us 180 degrees minus, we have C2. C2 is X. You can just use a plus when you factor out the minus. C3, which is Y, G2, which is X as well. So you have this, which gives us 180 degrees minus, into that we have 2X plus Y. That's how it looks. So this is 180 minus what? Minus 2X plus Y. That's the angle. But now, remember, that's just A2. And what did we say we are looking for? We said we want this whole angle, which is that, the angle CAE. So the angle CAE will be none other than what? The angle CAE will be equals to the angle A2 plus A1. Alright? Do we have A1? Yes, A1 is X. A2 we just calculated to be 180 minus. If I expand that, I'm getting minus 2X. That minus Y. Plus A1, which is just X. Think about it. 180 minus 2X plus X is minus X minus Y. I can factor out the minus 1, which gives us what? Which gives us X plus Y. Then we can go ahead and say, oh, the angle CAE is equals to what? Is equals to the angle B. What was the reason? This was Tan-Cot theorem. So what we said, this tangent right here gives us that condition. So this is Tan-Cot theorem. So we have CAE, which we just calculated. So angle B is equals to 180 degrees minus X plus Y. Was that what we are trying to prove? Yes, it is. So we have successfully proven that AB is equals to AC. Why is AB equals to AC? Those are sides opposite equal angles. Ta-da! Alright, easy stuff. I think this should be the last problem. This thing is forever going on. In the diagram, Pn is a diameter. Oh, I love diameters. Let me go and mark that. Where is it? Pn is a diameter. It's right here. Whew. What the heck? So Pn is a diameter there, which gives us that 90 degrees right here. So this is a 90 right there. Right. The circle has a center O. RT is a tangent. Oh, tangents. Favorite. So if that is a tangent, then it means the angle between a tangent and a chord is equal to the interior opposite angle. This is equal to that. RT produced, yeah, this one's OT is perpendicular to what? Oh, now they are bringing that theorem 1. You can see a line drawn from center perpendicular to, sorry, a chord. So it means this line will be equal to that line. Now this should be tough, but not as tough as us. Prove that TO is parallel to RP. Where's TO? Prove that this is parallel to what? To RP, sorry, that. So you think about all the reasons that can make you conclude. You need all of those, but we already have that. Remember we said that angle R, PRN, angle PRN is equal to 90 degrees, right? Which is R1 and R2 anyway. These are angles on a diameter, right? So that's what we have. But if you look at this, we were given that OT is perpendicular to RN, which means OSN, the angle OSN is also equal to 90 degrees. Why? These are angles on a straight line. If you don't want to use that, then you could have easily used that reason. Where? Perpendicular. OT is perpendicular to NR. You could have said OT perpendicular to NR. Like that. It's still fine. But now we just proved that the angles that are in corresponding positions are equal, which means this should be parallel to that. So, what are we proving? TO. Right. TO is equals to what? Right. So we have that TO is parallel to RP. Why is that? Because corresponding angles are equal. First part done. It is further given that TRN, where's TRN? TRN is equals to X, which is R3. That's TRN, yeah. R3. Name two other angles that are equals to X. The first one we've already found, which is angle P. Angle P is equals to what? Angle P is equals to angle R3. And they are both equals to X, and this is turn chord. Right, so this should be the turn chord theorem. Like that. Okay, now I always do this. After finding one angle, I just said this is equals to that. Now the question is, which other angle is equals to this now? So I make it a sequence. If I find that if this is equals to that, then which one is equals to that? And we just found it. It's there. It's looking at us. Right? How? We just proved that this line is parallel to that, which means this angle and that angle are equals to each other. So angle O3 should be equals to angle P, and they should be both equals to each other, equals to X, sorry. So those are corresponding angles since O2, not O2, OT is parallel to PR or RP. There, answered the question, right? Name two other angles. Prove that NTRO is a cyclic quad. So prove that this whole thing right here, let's highlight it first so that you can see. NTRO. So this one is a cyclic quad. We need to prove that this thing is a cyclic quad. How can we prove that this is a cyclic quad? There's multiple ways, but like I said, this is already proven. That's why it's 2 marks. Right, if we can prove that this angle O3, which is subtended by that line NT, is equals to O3, which is also subtended by that line, then we have succeeded. But remember, we just said we just proved that O3 is X. So for the mere fact that this is equals to that, number 3, we have that angle O3 is equals to angle R3, and they are both equals to X, and this was proven in the previous statement. Then we can conclude that therefore NTRO is cyclic. Why is it cyclic? Because we have what? Angles in the same segment are equal, or converse. Now it's the converse of what? Converse angles in the same seg. Alright. And then number 4, calculate the size of angle M1 in terms of X. Angle M, not angle M1. There's X. Angle M is far outside. Right, it's operating outside. Now we need to think, How do you think about this? Look at all the broader triangles. There's multiple triangles which M is part of, but the one which looks like is easier, it's the one which extends from here, goes to M, and then goes to that. Right, it goes through there. So this is the one which is easier, because at first we can find this angle right here. We can find out that the angle PRN, angle PRN is equals to 90 degrees. This was proven in question number 1, so I don't have to repeat it. This is proven. In fact, we also proved that. In fact, we can find the whole of R, this whole angle. That R is going to be 90 degrees plus X. It's this 90 plus that X piece on the other side. It's 90 plus X. Right, no reason needed for that. And we do have angle P. Remember, we proved that angle P is also equals to X in the previous statement, which means if we do sum of angles in that triangle, we will see that whenever we add angle M plus angle P plus angle R, they should give us 180 degrees, and these are angles in a triangle. Right, and yeah, that's that. What is M? We don't know M, but we know P to be X. We know R to be 90 minus X, which is equals to 180 degrees. Right. Yeah. It's now this now. Oh, this is plus X. It's not minus X, which means M is going to be 180 minus the 90 from that side. X plus X, which is 2X minus 2X. 180 minus 90 is 90, so that's 90 minus 2X. So this is equals to 90 minus 2X. 90 degrees minus 2X. Show that NT is a tangent to the circle at N. NT is a tangent. Show that NT is a tangent to the circle at what? To this whole circle at that point N. Basically, in simple English, they are asking you to prove that N2 is equals to P. But we know. So basically, you are trying to prove that what? N2 is also equals to P. But we know angle P, that angle P is X. Famous question, why? Why is N2 equals to X as well? Because we are trying to prove equality. Why is N2 equals to X? We need to figure that out now. Let's think. Why is N2 equals to X? How many marks? Just a 3-mark question, which means we have to think but not think too deep. Okay. Let's talk about it. Why is N2 equals to X? Let us not forget that we have a circle here. There was a cyclic quadrilateral somewhere here. So that one can also be used. Because at this point, I'm seeing the following, right? I'm seeing that this N2 is equals to O2, but the issue is I don't have O2 as yet. Is there a way to find O2? No, there isn't. At least I don't see it. How can we work this? Okay, that's not tangential. How can we find N2? I need a way to find N2. That's X there. Oh, you know what we can do? Since we have this line right here, ON is a radius, we can see ON is a radius, and they want us to prove that this is a tangent. Another option would be if we can prove that the angle N1 when added to N2 gives us a 90 degrees. If we can prove that this is 90 degrees, remember a tangent will always meet a radius at a 90 degrees. That's one of the options. Okay, so we have N1. Do we have N1 though? Do we have N1? Wait, yeah, we do have N1. We can calculate N1. Look at that triangle OSN. In triangle OSN, we have the following. O3 we calculated, we found X. Remember, it's equals to that. We have a 90 there. So N1 will be equals to 90 minus X, sum of angles in a triangle. Right. Now, in order for N1 and N2 to add up to 90 degrees, it means N2 must be X as well. And I think this is what we were struggling to find. This is what we had initially. Alright, it's what we had in our previous stage. But this is parallel to that. Fine faking. Do we have any cyclic quadrilaterals? But why though? Prove that this is a tangent to that. N2, this is subtended by that. Alright, prove that the circumference, maybe, just maybe. What if I try to find O2 first? Because I don't see my game plan now. Let me remove this. Because what I'm seeing right now is that I have an X there, right? And also, for the mere fact that OP will be equals to OR, this will be equals to that, and that's a radii. It simply means that also R1 will be equals to X. R1 will be X, and those are angles opposite equal sides. So from here, I can then work it out. How? I can find O1, sum of angles in a triangle. O1 will be 180 degrees minus x, so it's 180 minus 2x. And these are angles in a triangle. It's getting longer now. But this will allow me to find O2. So in this straight line right here, as you can see, we can have what? We can have angle O2, which will be equals to 180 degrees minus O1 plus what? Plus O3. Right, so this will give us 180 minus, what is O1? O1 is 180 minus 2x. What is O3? O3 is x. So this is the same as 180 minus into 180 minus 2x plus x is minus x. When we expand this, we get 180 this times that, which is minus 180 this times that, which is x, and this cancels that. This is what we were looking for. We're trying to find this x so that when we have that x, we can prove that the angle N2 is equals to the angle O2, and they are both equals to x, angles in the same sec, and then we are done. Right, yeah, you can do whatever. You can go back to that statement of N1 and N2, whereby angle N1 plus N2, remember N1 was calculated to be 90 minus x right here. It's 90 minus x, N2, which is calculated to be x right here. This cancels that, it's equals to 90 degrees. Then you can conclude that that's a tangent. Why? Because those two meet at a 90 degrees. Right, if not, then you can you use converse tan chord theorem? No, you cannot. It's quite impossible. Yeah, I think that's it. Here's another one. Name 4 angles equals to x. Yo, what's the statement? I think I cropped it out. Oh, it's there. In the diagram below, two circles touch each other externally at point P. That's the point where the two circles intersect. QPR is a common tangent. Hey, tangent, Baba. This is a tangent. Don't make it that big. So we have a tangent right here. At point P. EDRC is a tangent to circle PBFC at C. Wait, let me read that again. Doesn't make sense. EDRC. What is EDRC? Oh, this is a tangent to the other circle. So this is another tangent to that circle. Right. This one, RCA is equals to y and what? And that. Let's use the tangents first. If this is a tangent, tan chord theorem tells me that this triangle right here, this angle right here should be equals to that. So this is also equals to x. Right, and if this is equals to x, vertically opposite angles, do you remember them? The angles that are vertically opposite to each other are equal. If you look at this, you will see that this is vertically opposite to P5. So it means this will also be x. But if I have that from the tan chord theorem on the other side, this angle is equals to that. So this is x as well. Just in case. Name 4 other angles equals to that. So we've found one. We've found angle P1, which is equals to x. No, angle P1, let's write it well. Angle P1 is equals to A1. There equals to x on what? On tan chord theorem. Like that. Okay. And we have angle P5. Angle P5, which is equals to angle P1, which they're both equals to x. And these are vertically opposite angles. So it's vert-op angles. But from then we were able to prove that angle P5 is equals to angle C2, and they are both equals to x on what? Again, this is tan chord theorem. Alright. What else? We need the last angle. How can we find the last one? parallel lines. I'm seeing parallel lines. If I have, oh, even with parallel lines, we could have proved that since this is parallel to that, alternating angles, these two, right? Where can we use that again? Seems like there's nowhere else. The fourth angle, where is the fourth angle now? I'm lost. Statement. Is it going to help me anyway? Nope. Doesn't seem that helpful. Where's the fourth angle? This, no? Calculation. Yeah, maybe we have to calculate it. Sometimes you have to calculate the last one. This doesn't work out. Ooh. And name 4 with reasons for 7 marks. Yes. Let's blink. Let's think. Oh, there's the fourth one. Because if you look at this, you will see that this angle right here is subtended by that chord, this one, but the very same chord goes on to subtend another angle, both at the circumference. So that's angle E. Angle E, which is the last one. Angle E should be equals to angle A1 and it should be equals to X. Those are angles in the same sec. Okay, so this is X as well. Moving on, show that EPA is equals to X plus Y. Where's EPA? Let's mark that in bold. EP. Show that E is a E. Yo, it's E. Right. And this is E. That's P. And there's A. So basically they're looking for this angle and show that is equals to X plus Y. Before I even attempt this, let me find another angle that's equals to that. The very same chord goes on to subtend angle D1. Right, at least now I have this. Let's think. Those two are equals to each other. Point P is complicated. There's 8 angles at P. I don't even want to try play with that. I'm going to try find D1 first. If I find D1, then I have that. So now let's think. How can we find D1? First of all, we were told that this is parallel to that in the statement. And in fact, this whole angle right here is X plus Y. So we can find angle D1. Angle D1 is equals to what? Angle D1 is equals to angle C. The whole of angle C. But C is C1 and C2, which makes it X plus Y. Right. And these are corresponding angles. Since the lines AD is parallel to PC. Alright. Then once we have this as X plus Y, then by default we can see that angle D1 is equals to angle P7 like we said. And these are what? Then both of them should be equals to X plus Y. Again, these are angles in the same sec. They are both subtended by the arc AE in the same sec. There. Proven. We are done.